Reality has a flaw. Beneath atoms, beneath quarks, beneath everything we can measure directly, there exists a limit to how finely you can divide space and time. At this boundary, 100 billion times smaller than a proton, the universe stops behaving like the smooth, predictable stage you experience and transforms into something that looks more like boiling chaos. Physicists call it quantum foam, and it represents the most extreme environment we can theoretically describe. Space and time themselves are no longer fixed concepts here. They fluctuate. They bubble. They twist into shapes that shouldn't exist according to classical physics. This isn't speculation or metaphor. The mathematics of quantum mechanics and general relativity, when pushed to their absolute limits, predict this seething texture at reality's foundation. Understanding quantum foam means confronting what space and time actually are when you zoom in far enough that the universe can no longer hide its deepest strangeness. The frontier of quantum foam exists at the Planck length, approximately 1.6 times 10 to the power of minus 35 meters. To grasp how small this is, imagine shrinking a human to the size of the Planck length. An atom, by comparison, would be as large as the entire observable universe. We cannot build instruments to observe this scale directly. We never will. The energy required to probe distances this small would be so concentrated it would collapse into a black hole, destroying the very thing we were trying to measure. Yet physicists can calculate what must happen there by combining quantum mechanics, which governs the very small, with general relativity, which governs gravity and space-time. These two theories have never been fully reconciled, but they agree on one thing. At the Planck scale, their predictions explode into infinities and contradictions. Quantum mechanics says particles exist in fuzzy probability clouds. General relativity says mass and energy curve space-time itself. Smash these ideas together at the smallest possible scale, and you get a situation where space-time cannot be smooth. It must fluctuate wildly, like an ocean surface during a storm. Except the ocean is reality itself. Even in what you consider empty space, quantum mechanics insists something is happening. The vacuum state is not empty. It seethes with virtual particles, pairs of particles and antiparticles that pop into existence from nothing, exist for infinitesimally brief moments, then annihilate back into nothing. This happens because of Heisenberg's uncertainty principle. You cannot pin down both the energy of a system and the time it takes to measure that energy with perfect precision. The smaller your time interval, the larger the energy fluctuation you can borrow from the vacuum. At the Planck scale, these energy fluctuations become so extreme that they generate enough energy density to significantly warp spacetime. A virtual particle pair appearing at this scale carries enough mass energy concentrated in such a tiny region to create microscopic black holes and wormholes. These structures appear and vanish faster than 10 to the power of minus 43 seconds, the Planck time, which is how long it takes light to cross a Planck length. This is quantum foam, a roiling froth of appearing and disappearing geometries, where the distinction between space, time, matter, and energy dissolves into pure chaotic flux. General relativity tells us that space-time is a fabric that can bend, stretch, and ripple. Massive objects create dips in this fabric. Light and matter follow the curves. But fabric implies continuity, a smooth surface you can trace your finger across. Quantum foam suggests this picture fails catastrophically at small scales. Instead of a smooth manifold, space-time might resemble a foam of quantum fluctuations, with topology constantly shifting. Imagine filming the surface of boiling water, then zooming in until individual bubbles become visible. Zoom further and you see smaller bubbles forming on the surface of larger ones. Keep going, and the distinction between water and air, between inside and outside a bubble, becomes ambiguous in the turbulent interface. Quantum foam operates similarly, except the bubbles are microscopic black holes, wormholes connecting different regions of spacetime, and closed time-like curves where cause and effect lose meaning. The geometry of space is not fixed but probabilistic, a superposition of all possible shapes that could exist, given the energy density present. Our smooth, predictable spacetime emerges only when you average over countless Planck-scale regions. The same way a beach looks smooth from a distance, despite being made of individual grains of sand. No experiment has ever detected quantum foam directly. No experiment ever will. The problem is fundamental. To resolve details at the Planck scale, you need to probe with particles carrying enormous energy, packed into incredibly tiny spaces. These conditions inevitably create black holes that swallow both your measuring device and the information you sought. You cannot get data out of a black hole. Even if you could somehow build a Planck-scale microscope, quantum mechanics itself would prevent you from using it. The very act of localizing something precisely enough to see quantum foam would inject so much energy that you would create new foam, obscuring what you wanted to observe. It is like trying to study a calm pond by throwing boulders into it. Despite this, we have indirect evidence that something strange happens at extreme scales. When physicists calculate the vacuum energy of empty space using quantum field theory, they get an answer that is 10 to the power of 120 times larger than what we observe as dark energy. This discrepancy, the worst prediction in physics, might be related to quantum foam effects that we do not yet understand. Additionally, some theories predict that quantum foam could leave subtle signatures in the cosmic microwave background radiation, or cause tiny violations of Lorentz invariance, the principle that physics is the same regardless of your velocity. Experiments are searching for these effects, but so far quantum foam remains a theoretical prediction waiting for confirmation. If quantum foam is real, it fundamentally changes what space and time mean. They are not the stage on which physics happens. They are emergent properties, statistical averages that appear only when you look at large enough scales. At the Planck scale, asking where something is or when something happens becomes meaningless because space and time themselves are fluctuating. This has profound implications. Black holes might not be permanent prisons, but temporary structures in the foam that eventually evaporate, releasing their information in ways we do not yet understand. The Big Bang might not be the beginning of time, but a transition point where our classical notions of space-time emerged from a more fundamental quantum state. Wormholes, usually relegated to science fiction, might be constantly forming and collapsing in the foam, though far too small and short-lived to use for travel. Some physicists speculate that quantum foam could be the substrate from which consciousness emerges, though this remains highly speculative. Others suggest it might explain why the universe exists at all. Quantum fluctuations in a primordial foam could have triggered the Big Bang itself. These ideas push physics to its limits, where mathematics and philosophy blur together. We are trying to describe something that, by definition, cannot be observed directly, using tools that break down at the scales we care about. Quantum foam is a symptom of a deeper problem. We do not have a complete theory of quantum gravity. General relativity describes gravity as curved space-time, a smooth, continuous field. Quantum mechanics describes everything else as discrete, probabilistic, and uncertain. These frameworks contradict each other when applied to extreme conditions like black hole interiors or the Planck scale. Quantum foam emerges from naive attempts to apply both theories simultaneously. But those attempts produce nonsensical infinities. Physicists have spent decades trying to solve this. String theory proposes that particles are not points, but tiny vibrating strings, and that space-time itself has extra dimensions curled up at the Planck scale. Loop quantum gravity suggests that space-time is not continuous, but made of discrete loops, a quantum fabric with a Planck scale weave. Both approaches tame the infinities and provide mathematical descriptions of quantum foam, but neither has made testable predictions we can verify with current technology. Other ideas like causal set theory and emergent gravity take different approaches, but all agree on one thing. At the Planck scale, space-time as we know it ceases to exist in any meaningful way. The foam is what remains when you strip away our familiar classical approximations and confront reality's true quantum nature. You exist on the surface of quantum foam, completely insulated from its effects by scale. Every particle in your body, every atom in the room around you, is vast compared to the Planck length. The smooth space-time you experience is an average over incomprehensible numbers of foaming quantum cells. It is similar to how a newspaper photograph looks like a continuous image until you examine it closely and see individual dots of ink. The smoothness is real to you because you cannot resolve the underlying structure. This is both comforting and unsettling. Comforting because quantum foam, if it exists, has no direct effect on your life. The foam churns endlessly beneath reality, but its influence is diluted by scale, leaving the macroscopic world stable and predictable. Unsettling because it suggests that the solid, dependable universe you inhabit is built on fundamentally uncertain, chaotic foundations. Space and time are not what they seem. They are emergent illusions, useful approximations that work only because you are so much larger than the Planck scale. The universe does not rest on bedrock. It floats on foam, all the way down, with no final answer to what exists beneath. This is where physics currently stands. Confident in the mathematics that predict quantum foam, unable to observe it directly, and working toward a deeper theory that might explain not just the foam, but why there is something rather than nothing at all.